The end behavior of a polynomial function is determined by two key characteristics of the polynomial: its degree and its leading coefficient. The end behavior of a polynomial describes what happens on the two ends, far to the right and far to the left, of the polynomial. Visuals like the one you see here can be a little misleading. It makes it look like any function that has an odd degree and a positive power is going to have this wavy look to it. But the truth is that those two conditions really only guarantee what's happening on the two very ends of the graph. We could see multiple maxima and minima in between those 2 points, or those two outside designations, the far to the right and the far to the left. We could see multiple bumps, valleys, peaks. Lots of different things can happen in between those two ends. So when we talk about end behavior, we're really not describing anything in the interior of the function. We are describing everything on the exterior of the function. Now, what's described here in this visual here are the four different situations that can occur. What happens when the degree is odd and the leading coefficient is positive? What happens when the degree is odd and the leading coefficient is negative? An even degree with a positive coefficient and an even degree with a negative coefficient. Now again, there can be an unlimited number of peaks and valleys in between these end behaviors on the left and on the right. This is only guaranteeing us the shapes for the outsides of the graph. The reason that we're able to do this lies in these designations right here. What's happening as x gets obscenely large and very small in the positive and negative directions, respectively. You could imagine that if your degree is odd, something like x to the third, x to the seventh, x to the 11th, that if you input a very large positive number, you're going to get out a very large positive number. And if you input a very large, in absolute value, negative number, you're going to get out a very large, in absolute value, negative number. That's why the degree being odd matters to us, because when we have an odd degree, the possibility exists that we could get a negative result out of the evaluation of the function. If there is a negative in front of that odd powered term, then everything flips. The positive inputs, which are down here, will give us negative outputs, and the negative inputs will give us positive outputs, and we get that flipped over version of the graph. Thanks to the odd power, the odd degree, and that being the dominant power in the long run, that supersedes everything else. So even if there's an x to the 7th, followed by an x to the 6th, an x to the 5th, an x to the 4th, an x to the 3rd, an x to the 2nd, and an x, those terms in the long run don't end up mattering. The only one that ends up mattering is the one that's in the front when it comes to end behavior, because that term will be so much stronger than the others that it will just override everything else. Some functions, it's really hard to see that end behavior. Some it's not. We're going to look at a couple of examples. Now let's talk about the even powers. Situations numbers 3 and 4. In these situations, something like x squared, x to the 4th, x to the 6th, and so on. In these situations, we anticipate that regardless of the number that we put in the long run, we're going to get positive results. And that should make sense. When you square something, you raise it to the 4th power, you raise it to the 6th power. Regardless of whether or not it's positive or negative, you should anticipate a positive result. That doesn't mean that we can't have places where the function has a value of less than 0. Depending on the other terms in the expression close to the y-axis, you may end up with places that are less than 0. But again, end behavior only talks about the long term. It doesn't look at the short term. In the long term, these terms will become so strong that they'll just override everything else. And as you might imagine, the same thing that happened for the odd degree negative leading coefficient happens for the even degree negative coefficient. And that's what's over here. As we input x's that are very large or very small in the negative direction, very large but absolute value-wise, we get results that are pointing down towards negative infinity. We get these pointing down. You probably have some experience with an upside down parabola. This is what they're referring to. We're putting a negative in front of that even degree, and we're forcing those results to go the other direction. And we get inputs, regardless of the input, we get outputs that go off towards negative infinity. One more time before we look at a couple of examples of this. This is not to suggest that the insides of the polynomials could look very different from polynomial to polynomial. You could design polynomials as complicated as you want that would have certain numbers of bumps and peaks and valleys. That's not what this is doing. End behavior is only looking at the outsides of it. So here are two examples that we could use to begin the conversation. Here we have a leading coefficient in f of 9, which of course is a positive number. And this polynomial has a degree of 3. So referring back to our grid, we have a positive leading coefficient and an odd degree. And we should make note of that we fall into category 1. So regardless of what the inside of the graph might look like, we should anticipate the right end pointing up and the left end pointing down. And if we go to the graph of this polynomial, that's exactly what we have. Here's our right end pointing up. Here's our left end pointing down. We get steeper peaks and valleys than we had in the other expressions or in the other visual. Not as deep as we had here, but it does end up looking like that a little bit. And that's okay. But it follows what we expect to happen. Really large x values, as this continues off into really large increasing x values, make this term very large. And as we go off towards negative infinity in this direction, and we use really small negative numbers, that's going to create a lot of very large in absolute value negative results. In our second example, we have a leading coefficient that is -3, that's negative. We have a degree of 4, that's even. So if we go back to our grid, we have a negative leading coefficient and an even degree. That's this category right here. We should expect our two ends to point down. And if we look at the graph, here we have our two ends pointing down. We can anticipate, after we identified this space in here as being where the interesting maximum might happen, we anticipate these two pointing down and continuing off forever. This term, as it gets larger and larger, is going to overwhelm these two. As x gets bigger and bigger and bigger, this term ends up becoming what's called the dominant term. That dominant term is the term that determines the direction of the graph in the long run.